What's up, peeps? I want to do Leetcode problems because I feel like today is one of those days where if I don't, then it contributes to perhaps some failures in my future. It's not that bad, but you know, it's better to know some now or do some now rather than go back from Sydney and feel like you haven't done it. Haven't done any, lost some skills. You don't want any of that, right? So, yeah, we're just gonna do some Leetcode problems. I should say that I didn't bring my keyboard today, so we're just gonna have to do coding the old-fashioned way. That is using my actual laptop keyboard and not my Epic Split Ergo Glove 80. So unfortunate for that. However, let's do a dynamic programming problem. Let's do word break. It's gonna be lovely. It's gonna be lovely. I want to do more of these. Let's see. I'm gonna move some of these elsewhere so that they don't block up the joint. Okay. Alright. Monkey type. You know, there's no need for me to monkey type now because I don't have my keyboard on me. However, I will do it anyway. Oh. Damn, nah, I'm not doing this. I refuse now because I need to look at my keyboard every time I'm hitting a key now, which is kind of sad. No. Equals. You know, like the equal sign? I'm not memorizing. Yeah, no, I'm not going to continue doing this, but yeah. Okay, let's try and do word break. Given a string S and a dictionary of strings, word dict. Return true if S can be segmented into a space-separated sequence of dictionary words. Hello. You are allowed to reuse words in the dictionary an unlimited number of times. You may assume all dictionary words are unique. So, given a string S and a dictionary of strings, so a dictionary of strings in this case is a list of strings. If it's a list of strings, return true if S can be segmented into a space-separated sequence of dictionary words. Yeah, okay. You are allowed to use words in the dictionary an unlimited number of times. You may assume all dictionary words are unique. So the question is word break. Okay. Apple, pen, apple. Apple, pen, ape is true. Explanation, return true because apple, pen, apple can be split into apple, pen, apple. Notice that we can reuse words and also not use all the words. Okay. Cats and cars. Cats, cat, sin, in, car. So cats, in, cars. So we don't have cars. See. How would you go about this? Right. How does one think about this? Also, I wonder how loud it is right now. Give me a second with the audio. Let me just check. Filters. Okay. I think that's slightly better. Joe farts. Yes, that's it. That's it. They line up differently. No. And I'm gonna have to just, you know, copy it, I guess. And close this. Why is this thing here? I don't want to move this inward. Okay. Let's have a think. Okay, so is there any way that I would perhaps do this in... How could I do this? Is there a way for me to think about this? How would you do it in a decision tree manner? Check if this substring of words, you need left and right pointers maybe? If this is in word dict, then... So is this a set? No, it's a list. Can you make it a set? I suppose making it a set wouldn't be a bad choice, right? Something to think about, right? But we'll go set anyways, set of word dict. Because it might make operations faster. Just say that for now. Oh yeah. Galactic past, yes, perhaps, you know, there is some sliding window approach to consider. Let's, so this is word break. Have a look. Neat code. If you reach the end to find a word, so, you know, if you have left and right pointers of a particular string, so the string of left to right plus 1, if in word dict, then perhaps you search whether the next substring can be broken down further. From right to... So this is right inclusive. So we just got to go plus 1 to the end. And the word dict. Now this word dict becomes a string, so maybe we'll call this word set. In word set. Word dict. Now, problem is though, what does this do? Fuck, I gotta close the window. It's so fucking loud. It's getting annoyingly loud. Okay. What do we think? If you do it this way, then it means that if you reach the end of the word without having found dictionary, you can return false. But then if you have, you would go to the next word, try to scan through and get a word. if there is no good solution, then false. Like, what if you get if R is equal to len of R, len of S, then you would return false as well, unless it is true as well, right? All right, well, let's see. So we can think of this as being in a while loop, while that, perhaps. Right. While R is less than this, you would do something here, which may be these. Yeah, so look, I'm probably going to say that's the best thing that I can think of right now. And we'll just have a look at the solution. Okay, subproblem. Let's just try and think of the subproblem. What would the subproblem be? You know, you have some string that can be smaller and smaller each time that you do more and more searches. So the subproblem is a smaller string, right? But how would that help us? That's the problem. Okay, so let's just look at some of these examples. Wow. Top-down dynamic programming. Dynamic programming hash sets. Bottom up. Try. Okay, let's have a look at this video explanation.
Hey everyone, welcome back, and let's write some more
loud.
neat code today. So today let's solve the problem word break. So we're given an input string and a dictionary of strings.
Okay.
Of strings called word dict, and we want to return true if and only if S can be broken up into separate strings such that every separate string in S is also found inside of our word dict. And we are allowed to use words from the word dict multiple times. So for example, let's say we're given an input string Leetcode, and we're given a word dictionary of words called leet and code. So obviously, in this case, we could split this string, right, into separate strings, leet, right, break it down in this middle position,
Leet.
and then the second string would be code, right? So clearly, this can be broken up into words that are found in the word dictionary, so therefore we are going to return true. Now, what if we took code outside of our word dictionary? Well, then in that case, this portion, leet, is a word, right? But we have no matching word in our dictionary for the remainder code. So in that case, we would have to return false. And, you know, let's say we had an input string instead called leet and leet again, right? So two leets in a row, would we return true? Yes, because we're allowed to use this word from our word dictionary multiple times, right? Clearly it matches this, and it also matches the first portion. Now let's start off with the brute force approach. How would we even structure a brute force solution? Well, there's actually two ways to do it, but one of them happens to be more efficient, and I'll tell you why. So one thing we could try for an input string like this one, we could check, okay, the first character, right? Basically the first prefix of this string L by itself, right? Is this a word that's found in our word dictionary? It's not, right? So let's try maybe the first 2 characters together are a word, right? That's not it either. We would try the first 3, right? Basically, we would try every single portion from the beginning until we found a matching word that does exist in our word dictionary. And we know that we are going to find one like this, right? The first 4 characters of the string are a word, right? So once we found that, what are we going to do? Clearly, we have a subproblem, right? We found a matching word for this portion, but now we want to know, can we break up the rest of this string with words from our dictionary? So that's kind of how we're going to do it, right? That's what's going to be the subproblem, basically. So instead of starting from the first position in the string, we would start at this position in the string and try to word break it. Now, in this approach, what we're going to basically be doing potentially is from every single starting position, right? We're going to check every prefix, right? So from the first starting position, we might also get, if this happened to be a word, then we would start at this position and then do the same thing for this, right? Every word starting here. So basically, we're going to try every word. How many different words are we going to end up trying? We're going to try, let's say n is the size of our string n, and we're going to try basically from every single starting position to the end. So that's going to basically be n times n. Now, we could also do it a different way. Instead of trying every single possible, prefix, let's just check every word in our word dictionary and see if that matches. For example, this first word is 4 characters long, right? So what we're going to do is we're going to check the first 4 characters in our string. Does this match this word? Clearly it does, right? So what does that tell us? That tells us now, we have the same subproblem as before. We're going to start from this next position now, right? And check. And from here, we're basically going to be doing the same thing, right? So we're going to check, is leet basically, the first 4 characters, does that match leet? This does not match leet, right? So now let's check the next word in our word dictionary and check, does that match the characters over here? It does, right? We found code. So this is basically another way to do this problem. Instead of checking every single possible prefix, right, of any length, what we're going to be doing is we're going to be checking every single word in our word dictionary as the prefix. So instead of being O of n times n, we're going to be doing O of n because potentially we are going to be going through every single starting position, but we're going to be multiplying by the number of words in our word dictionary, which is, let's call it m. And the reason why we're going to be doing this approach is because it's going to be a little bit more efficient. And the reason is they tell us below in the problem statement that the max size of word dictionary is going to be smaller than the max size of the string. So this is overall probably going to be more efficient. Now, this isn't going to be the overall time complexity. We are actually going to multiply it by another n, because when we're checking, for example, this string, when we're checking, does that match the first 4 characters here? That's also a n time operation because it could, potentially be the size of the input string s. So this is basically going to be the overall time complexity, n squared multiplied by m. So I'm just going to basically show you the same formula that I usually do. I'm going to give you a quick illustration of what the decision tree would look like. Then we're going to understand how we could cache that to eliminate repeated work. And then by understanding that, we're going to go to the optimal dynamic programming solution, the bottom-up approach, and then we're going to code that up. Usually the DP solution is a lot less code than caching. So we're going to be looking at our input string Leetcode. So I think that's a little bit better than Leetcode, wouldn't you say? So what the decision tree is going to be is we're going to start at the first position, right? For example, I equals 0. We're going to be keeping track of whatever index we're at, right? Because we know that if we can find a word, that matches neat, for example, then the subproblem is going to be, finding words that can match the remainder of the string. For example, if we did that, our I, instead of starting at index 0, would basically be starting at index 4, right? So that's what the subproblem is going to be. So really, we're only going to have one variable that we're keeping track of in this backtracking solution. And so remember, we mentioned we're not going to be doing it like this. We're not going to check every single prefix. We're going to have decisions in our decision tree based on the number of words that are in the word dictionary. So we're going to have a decision for neat, we're going to have a decision for leet, and we're going to have a decision for code. Yes. Now, what we're going to notice is when we try leet on here, right? Basically, leet is 4 characters. Therefore, we're going to check the first 4 characters of here, compare it. Does that match leet? It does not, right? We're just 1 character off, that first one. So basically that means we're not going to continue down this path. Now let's try code. Does code match the first 4 characters? Definitely not. So we're not even going to continue down this path
so
either.
true.
Of course, neat does match this, so we are going to continue down here. We're going to do 3 more decisions,
That's
basically
so true.
1 for every single word in our word dictionary. Now, one thing though is when we are starting here, we know we matched the first 4 characters, so by this point we are now going to be at I equals 4, meaning we're going to be looking at this part of the string. So as we can see, checking neat, that's 4 characters long, so let's check 4 characters starting from here. That's not matching, of course, so then we're not going to continue here. Leet, does that match over here? Nope, we're not going to continue down this path. Code, does code match this portion? Yes, it exactly matches. So therefore, we are going to update our I pointer again. Since we matched 4 more characters, we're just going to take I and add 4 to it now. So now I is going to be at 8, and 8 happens to be that exact position right after the end of the string, right? This is where index 8 is. Therefore, we basically know that we were able to match the entire string. Therefore, we know we can return true, right? Once we find a single true, that means we just terminate, we end the function, we can just return true, and the function is done. Now from this example, it might not be super intuitive why we would use a cache, but let's say we had another path in our decision tree that led us to, for example, index I equals 5, right? And let's say we used all 3 decisions in that path, and let's say none of them yielded the correct result, meaning we were not able to word break this string from starting at index 5. So then we would return false from this path, right? And we would want to cache that. We would want to say that, let's say dp of index 5, right? We would want to set that to false. Basically, what we're saying is if we ever reached this same function call, if we ever tried it again, maybe, this decision tree could be really big. Maybe there would be another path from, somewhere over
That's
here
very
where
interesting.
we tried index I equals 5 again. In that case, we would want to return false immediately because we saw from here there was no possible way to break it down. Therefore, we don't need to redo all of that work if we, try the same exact thing. So we discovered that our base case is going to be dp of 8 because 8 is the length of the string, basically, is going to be true, right? If we can ever get to that last index, we're going to return true. So what we're going to do is now do the bottom-up approach, right? We're going to go through every single index in reverse order, right? So we would start at the last character, which is position 7, right? And see, can we word break the remainder of this string? And we would try every single word, right? Like neat, does neat match this string? Well, they're not even the same size, right? If we tried to match neat on 4 characters starting from here, we would go out of bounds of the string, right? There's not enough characters. So of course, this is going to be false, right? It wouldn't match neat. It wouldn't match the other 2 words in our dictionary either. And that's obviously going to be true for dp of 6, dp of 5, as well. So both of these are also going to be false, right? Basically, if we started from 6 or if we started from 5, we would not be able to match any of the words in our dictionary. But now if we start here, index 4, so we're now trying to figure out dp of 4, is that true? Well, yes, it is, right? It doesn't match neat, it doesn't match leet, but it does match code. So we are going to set dp of 4 equal to true. So now let's keep doing it until we get to the first character. So now we're going to be trying from dp of 3, right? So starting from this character, are we going to be able to match any of these? Well, none of these words even start with a T, so of course we're not going to be able to match. So dp of 3 is going to be false. What's dp of 2 going to be? It's also going to be false because if we were to start at this character, this E, would we be able to match any of the words in our word dictionary? Of course we would not. And what about this position? If we started here, would we be able to match any
There's
of the
a bit of a
words
try
in our
problem.
word dictionary?
Prefix
Again,
try.
not. So dp of 3, dp of 2, and dp of 1 are going to be false, meaning we cannot word break this string if we start at any of these 3 positions, basically. Now we're finally at the result that we were looking for, dp of 0. Is dp of 0 going to be true? Well, let's take a look. So we're starting at
this
the
is so
first
true.
character
This
in
is
the
so
string.
good.
Can we match any of the strings? We can't match leet, we can't match code, but neat, it does match this portion of the string starting at
this is
index
too good.
0. So then the question becomes, we're asking, can we break the entire string starting at index 0? So now since we did match the first 4 characters, we want to know, were we able to match the remainder of the string, right? So we want to know, starting from here, were we able to match this string to words in our word dictionary? Now, this is why we computed this bottom up, right? Because this is index 4, right? Notice how we already computed index 4 over here, right? It's the one that's highlighted in green because it was true. We were able to do it. So basically the equation that we would use for this is going to be dp of 0 plus the length of the word that we were able to match with, and we know the length of the word neat is going to be 4.
Hold the frick up.
Basically the why we able to match the entire string starting at index 0. So now since we did match the first 4 characters, we want to know, were we able to match the remainder of the string, right? So we want to know, starting from here, were we able to match this string to words in our word dictionary? Now, this is why we computed this bottom up, right?
Yeah.
Because this is index 4, right? Notice how we already computed index 4 over here, right? It's the one that's highlighted in green because it was true.
Eric. Are you still using omnivore?
So basically the equation
not anymore
that we
because
for this is going to be dp
it's what's it called?
of 0 plus the length.
Sorry, wait. It's I haven't tried self-hosting it, but also it's been acquired by another company, so it's not free anymore. I think that was the complaint everyone on Reddit's talking about. So I'm not using omnivore anymore. Currently I'm not even using any, but I want to use Obsidian's own plugin.
The word that we were able to match with, and we know the length of the word neat is going to be 4. So basically we can replace this length of the word with 4. So 0 plus 4 is just dp of 4. We know that was true, so we can set dp of 0 equal to true. So this is basically the result, right? This is how we're going to compute it, and this is what we're going to assign dp of 0 to. And once we've done that, we've computed the result. We know we can return true for the overall function. So with that being said, let's jump into the code.
I wouldn't be surprised that it is such a pain to set up, so fair enough. Okay, let's do this in the 3 ways that he suggested. Okay, so word dict, got this. Okay. Instead of going it through like a string, what you could do instead is, so the word break for sure, this is important. Starting from some R, right pointer. It'll mean that for word in word that, I guess word dict, fine. So let's just say word right is equal to len of word, and this would give you the next section. The word itself, we got to check whether the string up until that right pointer is indeed correct. So if this is equal to word, then you can go down further. Else, return false. Right? What else? When do you ever return true? If, so you would return if length, this is the base case of S, len of this, if S is equal to the empty string, return true. Word is not defined? Yeah, for sure. Neat. All right. So if S is empty, return true. Word and word dict. R is equal to the len of the word dict. So that's just going to be, say, like 5. If S to 5. Good. Wait, let me see. Print R, print S of R. Neat encode. Print word. Neat, code neat. Or was it code neat? It automatically just returns false. There should be a condition. If word, if len of word, well, technically I can use R here. If R is equal to, is not equal to the len of S, turn false. Shit. Give me a sec. So R is the length of the word. If this length of the word does not equal to something, but that's always the case, right? So if right, don't need length in there. Neat. Not all done. Alright, epic. So, solutions wise, what do we have? Might be something that I just use as a crutch for now. And I'm fine with using it as a crutch. So def DFS I equals length return true for sure. If word is equal to word dict, for word in word dict, if I plus len of w is less than equal to len of s, and next word is equal to if the DFS true, then you return true. Otherwise, you return false for the DFS. Shit. And then a hash set. Why would you use hash set? Shit. Fair enough. Top-down dynamic programming, you use a memo. And this one's using a hash set. And then you can use a bottom-up dynamic programming. This is crazy good. And you can use a try. But if you do a bottom-up dynamic programming, set everything to false plus 1. Why is it len s plus 1 though? If dp len s is true, then you go backwards. Word in word dict. Still got the same conditioning. dp I is equal to I plus len w. dpi equals dpi plus len w. Whatever the result is of that. It's true. And it's only a one-step thing, I see. If dpi, then you break. So if that's true, then you would break. Wouldn't need to search any other word because you know one word exists. That does make sense. Okay, fuck it. I'm not gonna do the recursive approach. I'm just gonna go straight to dynamic programming. And this is nm times t. M is the number of word, t is the maximum. Alright, let's try and copy this solution. Let's just copy this solution. I'm gonna try to do this, like, yeah, this is gonna be on the side, but I don't want to use this. If we get stuck on it, we'll think about it. Alright, but let's go. dp 0, so dp is equal to false times len of s plus 1 dp of len s 1 to true for I in range -1 to s, but len of s minus 1 minus 1. We will say, we'll just add that here. So if len s 1 if I equals len s minus 1, return, or should I say dp of I should equal true if or word in words, word dict. Maybe I'll use a word. Word dict. S of 0. The string. Yeah, I'm thinking about it. I'm just thinking about it. No, let's part of the solution. Oh shit. If I plus len of s is less than or equal to len of s. If it isn't, then you return, or it's already false. I see. And s of I to I plus len of w is equal to w, because that is just the case. My phone is almost dead. I'm almost done here. Okay, so then dpi should equal to dp of technically it would be whatever the previous was. In this case, if it's true, it's always going to be. So couldn't you just say true then? No, because it wasn't true in the previous. Then you need to know. Okay, and then if TP is already true, then you would break. Hello Lucas, you're still in the pain of exams? Damn. Damn, bruh. I hope you're not hating it too much. Grind it out, man. How is Amazon like? Are you enjoying it? Yes. It is very cool. I've spoken to like lots of people now. And the team that I'm working with is something that I think I am enjoying. Right now with the people that are there, they're also pretty awesome. You know, we're having lunches and stuff like that. It was pretty sick. Pretty sick, I will say. I do like it. Alright, invalid. That's because yeah. Hell yeah. Alright. Whoops. God damn it. Computer's slow as fuck. Gotta go to this specific Leetcode problem. Testing my patience with this one. With my browser on this laptop. Also because it's slowing down because of the heat also. So it's a fat rip. In that respect. Ooh, it's like super slow. Crazy slow. Alright. So that's it guys. I might just call it a day. I will